In today's video, we'll look at the kinetic theory of gases. Before we learn about the kinetic energy of gases, there are a few assumptions that must be made about the gas. The following are: the number of molecules in the gas is large, and the average separation between them is large compared to their dimensions. The molecules obey Newton's laws of motion, but as a whole they move randomly. The molecules interact only through short-range forces during elastic collisions. The molecules make elastic collisions with the walls, and all molecules in the gas are identical. If we look at the energy of motion of a gas, we see that for a monatomic gas, translational kinetic energy is the only type of energy the molecule can have. So we see that translational kinetic energy is equal to 3/2 our Boltzmann's constant multiplied by our temperature. So, since translational kinetic energy is the only type of energy the molecules can have, we can measure the molecule's internal energy, which is given to us as 3/2 times nRT. We can find the speed of the molecules, which are expressed by our formula 3kb multiplied by our temperature divided by our molecular mass taken to the square root, or taking the square root of 3 multiplied by RT divided by our molar mass. And doing so, we're able to calculate the speed of the molecules. If we look at our first example, it asked us, what is the average kinetic energy of a molecule of oxygen at a temperature of 300 degrees Kelvin? So the only information we were really given was our temperature, which was stated to be 300 degrees Kelvin. And we're asked to find the kinetic energy of a molecule of oxygen. We know that translational kinetic energy can be found by taking 3/2 multiplied by Boltzmann's constant multiplied by our temperature in Kelvin. And since Boltzmann constant is a constant and we're given our temperature, we're able to find the average kinetic energy of our molecule of oxygen. So we take 3/2 multiplied by Boltzmann's constant, which is equal to 1.38 times 10 to the negative 23rd, multiplied by our temperature of 300 degrees Kelvin. We see that our average kinetic energy for our molecule of oxygen will approximately be 6.21 times 10 to the negative 21st joules of energy. In our second problem, it states that hydrogen molecules in the upper atmosphere, where the temperature is about 1500 Kelvin, have an appreciable chance of escaping the Earth's gravitational attraction. The escape speed for hydrogen gas is about 10.7 kilometers per second. Calculate the RMS speed of the hydrogen molecules at this altitude and comment on the presence of hydrogen gas in the atmosphere. So if we look at the information we're given that our temperature is given to us to be about 1500 Kelvin, and we're given that a hydrogen molecule molar mass is equivalent to 1.00794 for an individual hydrogen. Since we have two, we can multiply that by 2 to get a hydrogen's grams per mole, which is its molar mass. So we're trying to calculate the speed of a hydrogen molecule. So we'll use our VRMMS equation, which is equal to the square root of 3kb multiplied by our temperature divided by our mass. So since kb is a constant and our temperature is given to us, we have to calculate our mass of our hydrogen molecules. So we know that the mass of an atom can be calculated by taking the molar mass, dividing it by Avogadro's number will give us the mass of our atom. So above we found that the molar mass of hydrogen was 1.00794 times 2 is its molar mass, divided by Avogadro's number, which is a constant of 6.02 times 10 to the 23rd particles per mole. So when we multiply this out, we see that our moles will cancel and we'll be left with a value in grams, which will be 3.35 times 10 to the negative 24th grams. However, our mass has to be in kilograms. So for every 1,000 grams, we have 1 kilogram. So you see our grams will cancel and we'll be left in kilograms. So that the mass in kilograms of our hydrogen will be equal to 3.35 times 10 to the negative 27th kilograms. Now that we know the mass of our hydrogen, we can plug it into our VRMS equation. So we have 3 multiplied by Boltzmann's constant, which is a value of 1.38 times 10 to the negative 23rd, multiplied by our temperature in Kelvin, which is given to us as 1500 degrees Kelvin, divided by the mass of our hydrogen atoms in kilograms of 3.35 times 10 to the negative 27th kilogram. And when we take the square root of this, we see that our VRMS will be equal to 4,300 meters per second. So we have calculated the RMS speed of a diatomic hydrogen molecule in Earth's atmosphere. And if we were to comment on the presence of hydrogen gas in our atmosphere, we would say that since hydrogen has an escape velocity greater than Earth's atmosphere, it is likely to leave the Earth's atmosphere and not return. Since hydrogen molecules have such a low mass, it will have a greater velocity than larger molecules like water vapor or methane. This is why we only see hydrogen bound to heavier molecules like water vapor or methane in our atmosphere, and not by itself.